We know medieval engineers had Damascus steel, carbon nanotubes before microscopes, metallurgy beyond modern replication. But they also had better mathematics, specifically structural geometry, force distribution, stress concentration theory, before equations, before engineering degrees. They understood physics through observation and failure analysis. The square tower looks strong. Right angles, thick walls, massive stones, psychological impression of solidity. But it has a fatal flaw, a geometric weakness that concentrates force, magnifies impact stress by factor of 10. The 90-degree corner. This isn't an aesthetic choice. It's a physics problem, a stress riser, a fracture initiation point. Medieval engineers discovered this, not through theory, through watching their towers crack, through siege after siege showing the same failure pattern. Every square tower hit by Trebuchet. Cracks start at corners, propagate along mortar lines, eventually catastrophic failure. Round towers? Impact damage, yes. Surface spalling, but no crack propagation, no structural failure. The geometry prevents it. This transition, square to round towers, happened across Europe between 1150 and 1250. 1 century. Complete architectural revolution. Not fashion, not aesthetics. Pure engineering. Survival-driven design optimization. Physics defeating previous assumptions. The square tower is band geometry, not by law, by mathematics. By stress concentration factors that guarantee failure. Stress concentration, the corner multiplier effect. Stress concentration is mechanical engineering principle. Force applied to material. Distribution of that force through structure. In uniform geometry, stress distributes evenly. 100 newtons applied. 100 newtons spread across material. Manageable. In non-uniform geometry, stress concentrates. Same 100 newtons. But accumulates at geometric discontinuities. Becomes 1,000 newtons locally. Stress concentration factor. Represented as KT. Theoretical stress concentration factor. Ratio of peak local stress to nominal applied stress. Formula: KT equals sigma max over sigma nom, where sigma max is maximum local stress at discontinuity. Sigma nom is average stress across section. For a 90-degree internal corner in brittle material under tensile stress, KT is approximately 3 to 6 depending on corner radius. But that's theory. Sharp corner. Infinite stress concentration theoretically. Reality. Material fails before infinity. Practical KT for stone masonry with near zero corner radius, approximately 8 to 12, 10 times stress multiplication. The corner as crack initiator. Stone is brittle, high compressive strength, low tensile strength. Fails through crack propagation. Cracks initiate at stress concentration points. The corner, where stress is 10 times higher than average. Trebuchet projectile, 100 to 150 kilogram stone. Impact velocity, 40 to 60 meters per second. Kinetic energy, 80,000 to 270,000 joules. And that energy transfers to wall, creates stress wave, propagates through structure. At flat wall surface, stress distributes over impact area, maybe 0.5 square meters. Pressure, 160,000 to 540,000 pascals. Stone compressive strength, 30 to 100 megapascals. The flat wall survives. Stress is below failure threshold, but stress wave reaches corner, concentrates, multiplies by factor 10. Local stress, 1,600,000 to 5,400,000 pascals, still below pure compression failure. But corners experience combined stress. Compression on one face, tension on adjacent face. Tensile strength of stone, 3 to 10 megapascals. Factor of 10 lower than compression. The concentrated tensile stress at corner, 1.6 to 5.4 megapascals. Approaches or exceeds tensile failure limit. Crack propagation. Mechanics, once crack initiates, it propagates. Crack tip is new stress concentrator, sharper than corner. Stress intensity at crack tip, K equals sigma square root of pi A, where A is crack length. As crack grows, stress intensity increases. Crack accelerates. Propagates along weakest path, usually mortar joints. The corner crack becomes structural failure. Wall section separates. Tower integrity compromised. Repair is possible, but expensive, time-consuming, and under continued bombardment, recracks immediately. Historical observation. Medieval engineers watched this happen. Repeatedly. Every siege with square towers showed corner cracking. They didn't have KT equations, but they had pattern recognition. Corner equals crack. Every time. Predictable failure mode. Solution? Eliminate the corner. Remove the stress concentrator. Change the geometry. Not a simple modification. Requires redesigning entire defensive architecture, but survival demanded it. The square tower went from standard to obsolete in 1 century. Physics overruled tradition. The round tower solution. Deflection geometry. Round tower eliminates corners. Replaces discrete angles with continuous curve. Fundamentally different stress distribution. Curved surface mechanics. Impact on curved surface. Projectile strikes at angle, not perpendicular. Glancing impact. Force vector decomposes. Normal component, perpendicular to surface. Tangential component, parallel to surface. Normal component causes compression. Absorbed by material. Tangential component causes deflection. Projectile glances off. Energy partition. Compression versus deflection. Curved surface maximizes deflection. Minimizes absorbed energy. Compare to tank armor. Sloped armor deflects projectiles. Vertical armor absorbs full impact. Same principle, different scale. Stress distribution on curved surface. No corners means no stress concentrators. KT approaches 1.0. Stress distributes uniformly around curve. Trebuchet impact creates stress wave, propagates through curved wall, spreads circumferentially. Instead of concentrating at corner, stress dissipates around curvature. Multiple load paths. Redundant structure. Local peak stress. Only 1.5 to 2 times average, not 10 times. Factor of 5 reduction in peak stress. This keeps stress below tensile failure limit. No crack initiation. No propagation. Structure survives. Deflection angle calculation. Projectile hits tower at point P. Angle of incidence alpha measured from surface normal. For curved surface of radius r, any impact point has tangent creating angle with projectile trajectory. Typical trebuchet trajectory. 30 to 45 degree impact angle. Not perpendicular. Parabolic arc. Square tower flat wall. Full 90 degree perpendicular impact. Maximum energy absorption. Round tower. Impact at angle 30 to 60 degrees from normal depending on impact location. 30 to 60% energy deflected. The projectile ricochets, bounces away, carries kinetic energy with it. Tower absorbs only fraction. Geometric optimization. Optimal radius? Too large. Difficult to construct. Requires more material, vulnerable to mining, too small, less deflection advantage. Approaches flat surface behavior. Historical towers, 5 to 10 meter outer radius typical, 3 to 6 meter inner radius, wall thickness 2 to 4 meters. This ratio provides sufficient deflection angle for most impact trajectories, structural stability, reasonable material requirement. The curve isn't arbitrary. It's force-optimized geometry, developed through empirical testing, refined through siege experience. Secondary benefit, foundation. Load, curved structure distributes weight differently. Compression follows curve, creates hoop stress. Stone is excellent under compression. Curved structure stays in compression under vertical load. Square tower corners create bending moments. Tension develops. Stone is weak in tension. Round tower eliminates bending. Pure compression. More stable. Less likely to settle unevenly. Foundation loading uniform. Circular footprint. Spreads load evenly. Reduces point loads on soil. This improves longevity beyond combat. The tower survives not just sieges, but centuries of standing. She's 6 o'clock to 8:30. The blind spot problem. Geometric coverage analysis. Defensive effectiveness requires covering all approaches. No dead zones where attackers can work unmolested. Square tower geometry. 4 flat walls, 4 corners. Defenders position on walls. Shoot downward and outward. Problem, the corner. Archer standing on wall cannot cover directly below corner. Shooting angle blocked by tower itself. Create blind spot, dead zone. Attacker at corner base is safe from archer fire from that tower. Width of dead zone depends on wall thickness and parapet height. Typically 2 to 3 meters at corner base. This allows attackers to place ladders, dig under foundation, plant explosive charges, all without defender interference from that tower. Flanking from adjacent towers. Solution. Place towers close enough that adjacent towers cover each other's corners. If towers are distance D apart, archer range is R. Need D less than 2R for coverage. To typical arrow range, 50 to 80 meters effective. Tower spacing, 30 to 50 meters, provides overlap. But this requires many towers. More construction cost, more garrison requirement, more weak points in wall, and at steep angles shooting at adjacent tower's base. Arrow trajectory is difficult. Angle approaching 45 plus degrees downward. Round tower geometry. No corners. Continuous curve. Archer at any position covers section of perimeter. Multiple archers around circumference provide complete 360-degree coverage. Minimum dead zone, only directly below archer position. Width approximately equal to wall thickness. 2 to 3 meters. But multiple archers eliminate even this. 3 archers at 120-degree spacing cover entire perimeter except minimal overlap zones. Coverage angle calculation. Archer stands at radius R, shoots downward at angle theta from horizontal. Coverage extends to distance D equals R over tangent of theta from tower base. Steep angle theta equals 60 degrees. D equals R over 1.73, approximately equals 0.58 R, close to tower. Shallow angle theta equals 30 degrees. D equals R over 0.58, approximately equals 1.73 R, further from tower. Round tower. Every position around perimeter has coverage extending 0.5 to 2 R depending on shooting angle. Square tower. Corner position has 0 coverage for width approximately equal to wall diagonal. 1.4 times wall thickness. Murder holes. Both designs use machicolations, floor openings allowing downward shots. But square towers need machicolations specifically at corners. See structural weakness point. Opening in corner reduces strength further. Round towers. Machicolations anywhere on perimeter. No structural concentration. Easier to construct. No weakness creation. The round tower provides superior defensive coverage with less structural compromise. The historical transition, empirical engineering evolution. Square towers dominated early medieval period. 800 to 1150 AD, simple to design. Orthogonal geometry, easy to construct with available tools. She's early square tower advantages. Right angles simplify construction. Stone cutting easier, square blocks standard, layout straightforward, interior space efficient, square rooms, corners for storage, stairs along walls, psychological presence, imposing, angular, vertical, projects power visually. These factors made square towers default choice. Engineering preference absent siege experience. The siege experience. Crusades 1095 to 1291. Intensive siege warfare. On Europeans encountering Middle Eastern fortifications. Middle Eastern castles, already using round towers. Byzantine influence. Roman engineering legacy. Europeans observed, round towers survive bombardment. Square towers fail predictably. Specific example. Siege of Nicaea 1097. Byzantine walls with round towers resisted Seljuk sieges for decades. Crusader castles initially built with square towers. Crac des Chevaliers 1142. Initially square. Now after repeated attacks, rebuilt with round towers 1170 to 1190. Empirical modification. Lesson learned through damage. The transition period, 1150 to 1250 AD, 1 century, architectural revolution across Europe, existing square towers, reinforced, some rounded off, corners filled with rubble and faced with curved stonework, new construction, exclusively round or polygonal, 16 plus sides approximating round. England, White Tower of London, 1078 square. Conisborough Castle, 1180s, round. Clear transition. France, Château de Loches, 1020, square keep. Château de Coucy, 1220s, massive round towers. Same evolution. Germany, Goslar, 1005, square. Marksburg, 1283, round corner towers. Consistent pattern across regions. Independent convergence on same solution. Physics doesn't vary by culture. Engineering knowledge transmission. How did knowledge spread? Mason guilds, traveling master builders, siege engineers comparing notes. No written engineering texts in vernacular. Knowledge was practical. It's apprenticeship-based, demonstration and experience. But the lesson was clear enough. Square towers fail. Round towers survive. Build round. Economic pressure. Replacing failed towers expensive. Building right the first time cheaper long term. Military pressure. Losing castle means losing territory. Survival demanded best available technology. Within 1 century, the entire European defensive architecture paradigm shifted. Pure engineering driven by physics and survival. To construction engineering, building the curve. Building round tower is harder than square. Requires different techniques, different skills, different tools. Stone cutting, square tower, rectangular stones, uniform dimensions, simple cutting, consistent assembly. Round tower, trapezoidal stones. Each course requires different taper. Inner face narrower than outer. Stone cutting angle depends on radius. Smaller radius requires greater taper, more material waste, more labor, and each stone must be custom fit. Template-driven cutting, precise to millimeter. Otherwise, gaps create weakness. Centering and formwork, square tower, string lines and right angles, simple layout tools, plumb bob and level sufficient. Round tower, center point and radius. Compass-drawn templates, consistent curvature critical. Formwork for arches and doorways, curved wooden frames. More complex carpentry. Removed after construction. Spiral staircases common in round towers. Each step is wedge-shaped. All radii measured from center point. Errors accumulate. Small radius deviation at foundation becomes large deviation at top. Precision essential throughout. Scaffolding, square tower. Scaffolding attaches to flat walls. Holes left in masonry for scaffold beams. Simple rectangular platform. Round tower. Scaffolding must follow curve. Circular platforms. More complex joinery. More material required. Or internal scaffolding, built inside hollow tower. Rises as construction progresses. Dismantled after completion. Foundation requirements. Round tower foundation, circular. Load distributes evenly. Bearing pressure uniform. Can be shallower than square tower. Less excavation. Faster foundation construction. But must be perfectly circular. Surveying critical. Center point established precisely. Typically 1 to 2 meters deeper than surrounding wall. Extends below frost line. Prevents seasonal movement. Stone foundation graded. The largest stones at bottom. Gradually smaller upward. Creates stable base. Construction time. Square tower. 50 to 100 skilled masons. 2 to 3 building seasons. 6 to 9 months weather permitting. Labor estimate 5,000 to 8,000 man days. Round tower comparable size. 60 to 120 skilled masons. 3 to 4 building seasons. 9 to 12 months weather permitting. Labor estimate 7,000 to 12,000 man days. More labor intensive. But the superior defensive performance justified cost. Long-term value exceeds short-term expense. Material requirement. Round tower uses approximately 10 to 15% more stone than square tower of equivalent diameter. Extra material in curved wall. Less efficient material usage, but not prohibitively more. Some material saved in foundation. Circular foundation, smaller area than square foundation, circumscribing same space. Net material cost, approximately 5 to 10% higher. Small premium for significant performance improvement. The engineering trade-off. More complex construction. Slightly more material. Significantly better survival. Medieval builders made the calculation, chose survival, accepted extra cost. Siege testing evidence. Archaeological documentation. Archaeological evidence documents the square-to-round transition, physical proof in remaining structures and excavated ruins. Castle sites with mixed tower types. Château de Coucy, France. Original castle 990s with square towers. Rebuilt 1220s with round towers. Excavations show foundation changes. Square footings cut away. Circular foundations built over or beside. Stratigraphy reveals timeline. Carbon dating of mortar. Dendrochronology of wooden elements. Confirms reconstruction dates. Physical evidence. Square tower fragments show diagonal cracking from corners. Predictable failure pattern. Round tower sections, no corner cracks. Impact damage distributed across surface. No crack propagation. Documented siege damage. Château Gaillard, France. Built 1196 to 1198 by Richard I. Mix of round and polygonal towers. Show advanced design for time. Siege 1203 to 1204 by Philip II. Extensive damage documentation in contemporary chronicles. Archaeological excavation 2000s. Impact damage visible on walls. Trebuchet strikes identified by impact craters. Analysis. Polygonal towers, 16-sided near round, show surface spalling but no structural cracks. Earlier square sections of complex show corner cracking, requiring reconstruction after siege. Physical validation of engineering theory. Real siege conditions tested design principles. Trebuchet impact analysis. Modern forensic engineering of medieval damage. Reverse calculation of impact forces. Impact crater depth and diameter indicate projectile size and velocity. Estimate energy transfer. Stone projectiles, 80 to 150 kilograms typical. Impact craters 20 to 40 centimeters deep in limestone. Surface radiating cracks 1 to 2 meters. Flat walls, radial crack pattern from impact. No preferential direction, symmetric damage. Near corners, crack pattern asymmetric. Preferential propagation toward corner. Concentration effect visible. Round sections, radial cracks only. No propagation beyond immediate impact zone. Contained damage. Experimental archaeology. Modern reconstructions tested. Reduced scale trebuchets, stone projectiles, both square and round target walls built. Scale 1 to 4 models. 2.5 meter tall sections. Limestone blocks. Historically accurate mortar. Impacts recorded. High-speed cameras. Strain gauges embedded in stone. Force measurements. Results. Square corners show 6 to 8 times stress concentration, consistent with engineering theory. Round sections. Stress concentration factor 1.5 to 2 times. Dramatic reduction. Matches historical performance difference. Multiple impacts. Square sections develop cracks after 3 to 5 strikes. Round sections intact after 15 plus strikes. Quantitative validation of medieval engineering intuition. They were correct without equations. Observation-based science. Modern engineering validation. Finite element analysis. Contemporary structural engineering tools can model medieval tower behavior. Validate historical design decisions. Finite element modeling. Computer simulation of structure under load. Divides geometry into small elements. Calculates stress on each. Model parameters. Stone material properties. Masonry modulus 10 to 30 gigapascals. Compressive strength 30 to 100 megapascals. Tensile strength 3 to 10 megapascals. Impact load 100 kilogram projectile at 50 meters per second. Contact area 0.1 square meters. Impact duration 0.01 seconds. Force time curve applied. Model boundary conditions. Fixed base. Gravity loading. Pre-stressed masonry. Weight of structure. Square tower FEA results. Peak stress at corners. 15 to 18 megapascals tensile stress. Exceeds stone tensile capacity. Stress concentration factor, 8 to 12 times. Consistent with analytical prediction and experimental data. Crack initiation predicted at corners after first impact. Propagation along mortar joints and subsequent impacts. Fatigue failure predicted after 5 to 10 impact cycles. Matches historical siege duration before breach. Round tower FEA results. Peak stress, 4 to 6 megapascals. Below material tensile limit. No crack initiation predicted. Stress concentration factor. 1.5 to 2 times. Minimal. Stress distributes circumferentially. Surface damage predicted. Spalling of outer stone face, but no structural compromise. Failure prediction. 30+ impacts required. Triple the durability of square design. Parametric optimization. Modern analysis can optimize radius, test various curvatures virtually. Smaller radius, 3 to 4 meters, less material efficient, approaching flat wall behavior. Larger radius, 8 to 10 meters, diminishing returns. Deflection benefits plateau. Construction difficulty increases. Optimal radius, 5 to 7 meters for typical castle tower. Balances all factors. Matches historical dimensions. Medieval engineers arrived at same values empirically.